All right. So you had a little exam. It was not a big exam, little exam, and I'm very happy with your performance. It's a way to go. But some people still working on it, I hope. I have a couple of students in class that still did not turn in the exam, so I emailed them a reminder. So if you received a reminder, well, just send it to me, and that's all you need, right? So the exam we had on Tuesday, and I sent it a while ago, but then I resend it again, and I also posted it on the Brightspace to those of you that like Brightspace better than email. It is important, of course, to check email, especially if you're taking online classes. Sign up to online class and never check email is kind of odd, right? So, anyways, I will wait another week or so. So if there be no reply to my emails from those students that do not reply, I'll have to drop them. It's not my intent, but I don't want to fail anybody from those that did not take the exam. But anyways, if you took the exam, if you like your grade, it's perfect. I posted them on Brightspace. If you don't like your grade, well, do it again. I'll let you redo it again if you want to. I will regrade it again. It's not a problem. Anyways, if any questions, we can discuss that out after the class. If you wanna have any ideas discussed, please let me know. You can let me know that anytime. So we are through with section 8.2. We actually had it before the exam, and then I did not follow up on that. So maybe I'll do a problem and then move to the next part of the story because we're now heavily into integration exercises. So I didn't do any of these definite integrals. Maybe I'll do one. Let me try something like exercise number 49. Something not very bad, something pretty standard, and something that you have no choice but to use that new procedure called integration by parts. So I will be looking at exercise 49. It's a definite integral, and in that case, I will wait until the very end with those 0 and 3 limits. I need to take antiderivative first, and then I will plug it in. So e to the power of x over 2, you can and integrate and differentiate. That's great. When you say, Alex, you can also integrate and differentiate your variable letter x. Yes, but the problem is we gonna need to probably use the x as a part that we differentiate because it will disappear and that will make us very happy, right? And then the rest, which is dv, will be my other piece. So if I replaced my x with variable letter u, and then when I take its derivative, because one part will always differentiate, so that dx will be du. 1 dx is 1 du, and that's good start. And then the other portion, which is dv, right? E to the power of x over 2. Okay, so that piece will be integrated then. And when I integrate my dv, on the other side, I will have just a v. That's, oh, this is always going, and now I need to think of little substitution. Let me do it separately. So if you try to integrate e to the power of x over 2 dx. Just to make sure, because it looks like some people say, Alex, I'm not very clear of what you're doing. Well, I substitute. So that's something you need to do because, let's say, letter Z. Let change. Because all you can integrate is clean e to the power of x. So that's the one you can find the antiderivative, which is going to be exactly the same thing plus the constant, right? But now we have no x over 2, no clean power of x. We have x over 2. So take derivative. So that'd be dx times 1/2, or dx over 2, right? And that's dz when you take derivatives. And then, since you don't have that over 2 stuff, you will be, well, bringing the 2 to the other side. So multiply by 2 both sides, because that way you will be able to clearly replace your dx with 2 of those dz's, and then e to the power of, oops, letter z. I don't know what happened, I jumped. So now we take the antiderivative. So always the issue is with integral. So we get rid of that integral sign. So now we use the formula below because it's clean e to the power of z or x, doesn't matter. So now I will be taking care of that antiderivative and then use the original variable, but the 2, right? The 2 is still there. Right? The 2 is coming out in front, so the 2 is still there. And e to the power of, instead of z, I put x over 2. Just like that. Please notice that this will be used twice in the exercise that we're doing, times dx, not plus. Right, I need to wake up. Times dx, times multiply. Maybe I'll just get rid of that little spot and just have dx. Where is it? Dx, it's just a constant. I really need to wake up. Wake up, Alex. Wake up, call. So plus the constant. Right? And then put plus the constant, wrote some other stuff. So anyways, you took care of z, you replaced it just with x over 2. So anyways, why this is so important is because we now can integrate. We actually went through this whole process carefully here, and we saw that this is 2 e to the power of x over 2. When you say, Alex, where is your constant? Well, we are not done yet, so we don't want to use the constant as of yet, even though it's there, because we actually do have integral, right? So we already have, right, u times v minus, you see there is still integral, v times du. So to put the plus the constant is a little bit early because the plus the constant is also going to be here. So plus 1 constant plus another constant will give you plus 2 constants, and that's just a constant. So that's why people don't write that. So we now can see what comes out. So it's u, which is x, right? And v, which is that 2e to the power of x over 2. So this is the first piece. And then we need to subtract second piece, v, which is 2e to the power of x over 2 once again. So we'll be utilizing the same exact integration again, but the 2 will jump out. And then we need to multiply it by du, which is exactly dx. Okay, so we know what to do now. And let me put that first piece here. And then 2 can be in front, right? And then e to the power of x over 2 at the end. And then I need to subtract antiderivative. So antiderivative ended up being this piece, right? 2 e to the power of x over 2. But it's not just a 2, right? There is another 2. You see that other 2 that is multiplied by it. So let me put it in blue color. So better see 2. So the 2 needs to be also multiplied by the result. Now, I don't put plus the constant because we now have those limits of integration, 0 to 3. So you have to plug both of them in. So that's definite integral, and the standard procedure to end with this story will be here. So when I plug in 3, well, no, it's just instead of x, I end up with 3 over 2, right? The power minus, now I need to plug in 0. And please notice 2x will give us 2 times 0, so it'll be 0. Right? 2 times 0, whatever multiplied by 0 is 0. So that's good. Then I have to subtract 4 because it's 2 times 2. And then again, I plug in my number 3, so it'd be e to the power of 3 over 2. And then also I need to subtract that 4 multiplied by e to the power of 0 over 2. But that's not 0, because e to the power of 0 is 1. You know that? 0 power is always 1. So what I will get at the very end is a collection of like terms. 6 minus 4, I don't know why it jumps. 6 minus 4, which is 2, right? And that's 2 multiplied by e to the power of 3 halves. And then I'm multiplying 4 by 1, so it be just 4 with a minus sign. So not to hurry. That's the key goal for the calculus classes. Do not hurry. So easy to miss, do a little bit of arithmetic. So I would say this level of exercises are fine with the exams. I don't give you any harder problems. You probably already know. I know that on the last exercise, we had test and 2 problems with a square root and in denominator, and you had to complete the square. Some people did it, some people did not. So I want to make sure you complete the square. That's why I give a chance to redo that exam if you want to. If you're fine with your grade, then it's good. But if you want to, you can always fix it. Anyways, continue with more integrations. Now they call it as trig integrals. Well, we saw trig in the previous sections as well, but it's all about because of trig substitution, either sine or cosine. I guess here is a very nice example that tells you if you decide to substitute your sine as a letter u, right? That's what they're doing here. Instead of sine, they put u, so that'd be u to the 5th. But since derivative of sine is cosine, so that will be your du. And it's very nice to integrate, right? You 6 over 6, and then you put sine back. So the point of story, if you can see there are 2 different functions, sine and cosine, multiplied together, and if derivative of sine is cosine, then one single cosine is good idea to separate for your du. And when you substitute sine, you better write everything in terms of sine. Let me see, Alex, what should you say? Well, I guess it's better to look at the examples. Like here, for example, you can lower your power, like sine squared, you can present in terms of just cosine, no squares, or cosine squared also in terms of cosine, no squares. Those are formulas from trigonometry that actually come out from double angle identities. If you didn't take trigonometry a while ago, well, I guess just write down these two formulas. They are popular, but I don't think they go any further than this particular section 8.3. So the other formulas I don't think we really need to worry about, but I can take a look at example just to show you the usage. I think example 2 is very nice to look at. So let me maybe clear the mess. Stop share, share it again. So we already know that we should substitute either sine or cosine. So it'd be a good idea to substitute sine because it's inside the square root, right? So if it's inside the square root radicand, you're always trying to substitute it. So cosine, if it was just a single cosine, right, derivative of sine is cosine, then you would definitely feel good. But if you separate one cosine, there will be the cosine squared left. But cosine squared is same as 1 minus sine squared. So you write everything with respect to sines, and that's what enables you to integrate, because you'll have just function when sine is substituted, cosine will be derivative. So I think it's a good idea to trace this exercise. Pretty neat procedure. So analogous one is being done with tangents and secants, but I don't think it's as popular. I don't want to get real deeply into this. And there are some other interesting things that happen. So maybe I could just do a problem here. I don't want to get very deeply into this whole story because you can be stuck with this for a long time, technically, because again, there are so many exercises you can enjoy, of course. Or if you don't like this part of the story, then you don't enjoy them. So let me try one of those problems. Let me try, for example, number 11 exercise. Just do one. I don't want to spend too much time with the sines and cosines because problems are of pretty much the same kind. So it looks like if you substitute cosine, we say, why do I substitute cosine? Because it's inside the square root. Whatever is inside of square root or in denominator, remember that should be case of substitution. So I already have an idea. So if cosine or whatever, 2 thetas, okay, you replace with variable u. I say, Alex, why u? Well, they usually use letter u. You like some other letter y or z, it's fine, you can substitute. No. Derivative of cosine is negative sine, right? And then you have to multiply it by, because of chain rule, by derivative of 2 thetas, which is going to be 2. So it's actually going to be negative 2 times sine. And that's with d theta. And that's my d. So it turns out the power of sine goes away. First power of sine will go away, but there will be more powers, right? So that's why you should separate. So you write sine squared and 1 power of sine that will go away because it will be absorbed with your du. And then we have a cosine inside the square root, so I can say power of cosine is really 1/2, right? Because we want to write it as power to prepare to take antiderivative and then d theta. So again, please notice when I will be doing my substitution of cosine, then sine 2 theta and d theta will be replaced with du. Well, not exactly, because -2 is on the way, but I know how to take care of it. Just put -2 in denominator. Standard. So du over -2. And now we lack of a representation for sine squared. But instead of sine squared, we always put 1 minus cosine squared, Pythagorean theorem. Right? Sine squared theta of 2 thetas. So this stuff is what I'm gonna multiply by that stuff. So what powers do I get when I distribute? I started from the bottom and keep going up. I believe it's like is a Chinese way to do things, to write them down from bottom up, something like that. I'm not sure, but I think so. Maybe I'm wrong. So anyways, cosine to the power of 1/2, right? Cosine to the power of 1/2. I'll write it carefully. So better see it. 2 thetas. And then you multiply it by sine and d theta. So we'll split it into 2 integrals. Theta d theta. So that's when I distribute the first. And then when I distribute the second, it'll be minus, right? It'll be minus another integral, and then power of cosine, 2.5, right? Or 5/2 probably will be more convenient for anti-differentiation. 2 thetas, and again, times sine. So please notice that sine is clean with d thetas. It's all prepared in here for my substitution, because sine 2 theta theta is du over -2. So this is du over -2 as well as that. And we gonna end up with first piece, which is when you, again, substitute cosine as u. So that'd be u to the power of 1/2. Right? And then it's du over -2. That's my first integral. You see that? And then we still integrate. Then we have a minus sign, and then second integral now would be u to the power of 5/2. Right? And times again du over -2. And of course, there's an integral sign. Like that. And again, those are very nice little pieces, because I can use my favorite power rule for antiderivatives, just to add 1/2, just to add 1, sorry, add 1 and 1, so with 3/2, or 1/2 if you like, but I'd rather write it as 3/2 because it's convenient to put the same 3/2 in denominator, right? And it's multiplied by du over -2. Okay. We'll take care of constants after that. And now this -2 and the minus will give us a plus, right? And if you wish, you can put over 2 already. I say, why, Alex, this is du? Need to wake up, right? Wake up. I say, so what's There, du is gone. Well, just number one, right? And that's also going to be number one. Now, u to what power? 5 halves plus 1, which is plus 2 halves. So it'll be 7 of those little halves, and this is divided by 2. See, I didn't hurry dealing with those denominators, whatever complex fractions, because nicely they cancel as well as here, right? You multiply 2 by 7 halves is cancel. So just try to keep it simple. Don't go too far. So now the question is, where should I be next? So I guess this stuff should be separated here because now I have room on the bottom. So we'll write my answer on the bottom. So please notice the problems become lengthy, right? So this is u to the power of 3 halves. So instead of u, now I use the substitution. So that'd be cosine of 2 thetas. Right? Okay. And this is also raised to the power of 3 halves. So you can put just power, or you can put the square root because it's halves, and then cubed. So it's a cosine cubed. Make sure it's cube or cosine. Cosine cube. And we're still having the denominator that's 3. Right? And then we have a plus sign, and that's 1/7. So denominator will be 7. And I can also write it as a square root. Now that cosine will be raised to the power of 7. Okay. See, there's a bunch of numbers around, multiplied, divided, but we produce the answer. And of course, don't forget about plus c plus the constant. So that's the answer. It's tedious. It is tedious, kind of fun, but what did we do here? Substitution, and we just new derivative of cosine is negative sign. That's all. So it's not really much, right? Well, not really much of new stuff, but the problems may look kind of scary, and with those secant tangents as well, right? If you remember that derivative of a secant is a secant tangent, you could, maybe I'll do one more. Maybe 33, because that one is going to be longer. I'll do 33 just to give you an idea, because technically all of them either substitution of sine or cosine, or in this exercise we can substitute secant. Again, when I write 33, so I can put secant times secant tangent. Please notice I separated already secant squared with secant tangent, with secant times secant. Why? Well, because derivative of secant is secant tangent. Because I remember that. I know you have nothing else to remember. I know you have better things to remember, of course. So it's in the formula sheet. That's why I'm not going to be really heavy on this part of the chapter 8, but just to realize. So if you do the substitution, the whole goal of substitution is always the same. So if you substitute one as a u, the rest should be du. So if you substitute secant of x as u, then derivative of secant, which is secant tangent, secant on the right side, secant. See, that's why I don't like secants, because it's kind of annoying to write. For me, it's kind of hard to keep track. So it's a secant tangent. Feels like to write sine. Let me be careful. Secant tangent. Secant times tangent of x. Dx is d. Okay, looks like done with that part, and now we gonna enjoy because we ended up indeed with integral of u, that's first piece, times du, right? And that's just a pleasure to integrate. It's first power, so we're gonna add one, get second power, and put that same in denominator. And of course, plus the constant, and then over 2, now I'm gonna have not u, but secant, right? So it will be secant squared over 2 plus the constant. So we got it. Let's see, what is this for? Well, just to manipulate with trick formulas, I guess, and that's all I can say about it. So I'm not gonna really get into this because they being pretty heavy on that, and I don't think we need to worry about. And I will do another exercise from next section and end it for today because there is more trigonometry. And as I said, I'm not gonna be, as promised, I'm not gonna be real heavy on trigonometry. It turns out there's a substitution if you cannot find your antiderivative easily, because if you have a square root, usually you substitute your radicand, but then 2x is missing, and that's not going to be possible to use standard substitutions that we already utilized before. And standard substitutions, again, were either denominators, or if you have square root or cube root, radicands. And the derivative of that radicand needs to be the remaining piece, and it's not in the remaining piece because derivative of x squared is 2x, so there is not enough powers of x. And for that matter, sometimes you get to use trig substitutions. Again, it works only when you have a square root. If you had a cube root, it wouldn't really work. So the point of story, if you were to replace your x with either sine or cosine, doesn't really matter, because if you have 1 minus cosine squared, it's going to be sine squared. And why this is so important here is because we have a square root. So if you square root, you're going to end up with just a sine. So you're going to lose the square root. That's the whole point of this process. And you see, if you decided here, for example, to replace your x with a cosine, you will say y. Doesn't matter. Then when you take derivative of y, dy, derivative of cosine is negative sine, right? So if you decided to replace your radicand here like that, you're going to end up with integral of sine x dx, right? Sine x dx. And please notice that's actually dy, right? So it is actually going to be a negative dy. And that will give me antiderivative right away, and that'd be just great. So the point of story that you utilizing Pythagorean identities in order to get rid of the radical. And of course, it doesn't have to be starting with one. It could be starting with any number a. That's why they say we'll replace it with a squared. And then when you do a little bit of factoring things out, that a will go out, square root will leave you without the square. So it'd be nice looking. So I guess trig substitutions, when you subtract, you use identity called Pythagorean, or when you add, remember, there is another interesting identity. I just mentioned it. I know it's getting a lot of information, so some people start to feel they're just overloading you. So I'll just write the identity. Secant squared. Secant and tangent. Secant squared is 1 plus tangent. So if you have 1 plus, then you use tangent as your substitution. So for this case, you're going to end up substituting your letter u as tangent, and then you end up with secant squared inside the radical, and square root from secant is secant. And that's what they probably discussed somewhere down below. Again, if that's a, then you need to have factor of a in here, so you can factor a out, just like they recommend to do here. So it takes a little bit of writing, of course, but that's the main idea, so the formula. And the last case, u squared minus a squared, and that's going to be another case of the substitution, and that's something I will maybe slightly touch next time. As I said, I don't want to give you another section, because a little later we'll see that it's really, I don't want to use the word pointless, but it's never ending procedure, because we just noted if it was not the square root but the cube root, this would not work. And if that be any other order radical but square root, these trig substitutions are not going to be working. And for that matter, it turns out, on the contrary, with finding derivatives, when we have antiderivatives, there's just a very limited number of them that we can take. Derivatives you can take of any power, or any function, or any composition of functions, like square root cosine or cube root cosine minus 1 or whatever. If you take derivative, chain rule will take care of it. But we don't have a chain rule for antiderivatives. We have to do various substitutions. And that's the reason why eventually they just give up on this, and they say just too many possibilities. So please don't get disappointed. We'll probably discuss that next time or time after next. And at that stage, we'll give up on the integrals, say enough, because there are too many of them. So they actually created tables of integrals. If you're interested, we can find it somewhere. If I go to the search and try to find so-called table of integrals. I know we have table of integrals already that consists of not too many integrals, but there are actually tables of integrals that consist millions of them. Can you imagine? Millions and integrals. Science there. We'll just click the first one. How many they have? I saw the table was over than 3 million integrals. that they take. So with derivatives, we have no problem. The point is we can use chain rules, so we can take derivative of just about anything. Let me clean this mess. Stop sharing. But with antiderivatives, we don't have such a luxury. So they have a table of integrals. Looks like it's pretty short, but it's still way bigger compared to what we already have in the textbook. It's more than 100, right? So you can take any antiderivative. You don't need to do any substitution. Instead of A and B, whatever numbers we have there, you just want to plug them in and you get the answer, which is nice when you have a table, right? So you don't take antiderivative, you just find your integral in a table. And that's the point. But if you don't find the integral in the table, well, then you need to look for another table. So you can check and see in Google search, there are various tables of integrals. See, there are some printable tables that have probably millions of those, so you can just click on some of them. Table 18 and so forth. So there are various, because those are just basic ones, but there'll be more. And the message is we can't just take all those integrals. So we have differential equations class that tackles some more untakeable integrals that we cannot take in the calculus. So we go dig deeper and then again and again. So we just end up with huge tables. So some people are still working on them, probably using AI and other tools, and there is no end to this story, actually. That's why I guess I'm gonna put an end to this now. So I think I better stop this recording. And I want to say that I'm, again, pretty happy with most of you performance on the midterm. That's the way to go. So now you know how the final is going to look like. Pretty much same thing. I'll ask you a couple of questions and give you the whole day or days to think about this. So you will have enough time, and I'm sure you will keep your grade. If you like your grade, that'd be pretty much your grade for the whole class. But we need to, of course, take final in 8 weeks or so. So, of course, we'll discuss all that. And again, I'm letting you go. And those students that still owe me some work, well, please email it to me. I accept late work. Yes, I do. I accept it. So don't worry. And if you do homework, that's great. I will, of course, accept it later. That's fine. Just make sure you do it. Don't take too much time or weekend. Just show me whatever you've done. That'd be good enough. All right. But so don't get stuck with the old homework because we have new ones coming, right? But it's fine. It's fine. As long as you do it, that's great. It makes me happy. So email it to me at your own convenience. I will accept it. So anyways, if anything else, please let me know. And thank you for coming over. If there's nothing else, you can just have a good day and have a great weekend. And we'll continue next week on Tuesday. How about that? Next week we'll
All right.
do a
Thank you,
little bit more.
Professor.
Thank you. Bye-bye.